Hello, we are Posse Possumus.
I'm Angela.
I'm Paige.
I'm Wooba.
I'm Bill.
And I'm Eddie, and we are from Phillips Academy in Andover, Massachusetts.
Wildfires are becoming an increasingly devastating threat across the United States, especially in California. Since the 1990s, their frequency, size, and intensity have all dramatically increased, fueled by climate change, drought, and expanding human development. The 2025 Eaton fire alone burned the equivalent of 3 football fields per minute, causing up to $164 billion in damage, and placing it as one of the most costly disasters in United States history. These impacts also go far beyond flames. Economically, wildfires have destroyed homes, wiped out farms and vineyards, and destabilized insurance markets. Public health systems are overwhelmed by smoke-related illnesses, and long-term exposure is leading to chronic conditions. Ecologically, fires are degrading soil, reducing biodiversity, and making forests more vulnerable to future disasters. Social and political tensions are rising too, as recovery resources are distributed unevenly and legal disputes over land ownerships increase. Even national defense is affected. Fires around military bases and energy infrastructure expose new vulnerabilities. Worst of all, wildfire emissions feed a vicious climate cycle, making future fires even more intense. This study uses satellite data and modeling to better assess wildfire risks, helping shape smarter and more sustainable responses, because in today's world, managing wildfires means protecting lives, economies, ecosystems, and national security.
First, we need to talk about the data we will work with. We focused on 2 main data sets, the National Fire Incident Reporting System and the California Total Wildland Fire Stats. These are large, well-established sources that provide nationwide and regional insights into fire incidents. They cover everything from what caused the fire to how it was handled and the damages involved. We also looked into including wildfire insurance data to analyze how risk is priced. Unfortunately, we weren't able to find public data on this, so we excluded that piece from our model. Now, onto how we identified and organized the data. We essentially grouped our data into 3 categories: causes of wildfires, loss severity, and frequency of fire of time and space. First, we analyzed the causes of wildfires. This includes details like what ignited the fire and where it happened. This helps us understand risk patterns tied to human behavior and land type. Second, we also looked at loss severity. We used metrics like total area burned, total deaths and injuries, and financial loss. We also included response-related indicators such as how long it took to control a fire and how many people were involved. These help assess how quickly a fire can escalate if not addressed efficiently. Third and finally, we examined the frequency and probability of fires over time and space. This includes seasonal trends by quarter, meteorological conditions like wind and humidity, and how these factors interacted with historical fire events. From the dataset, we selected specific fields for modeling and did a lot of pre-processing. For example, we created new fields like alarm hour and incident season from timestamps. We also consolidated categories, like grouping similar fire causes or heat sources to simplify analysis. Meteorological data, like wind speed and temperature, were cleaned using outlier detection. Several fields, such as total loss or total value, had high missing rates, so we either binned them into categories or excluded them from parts of the analysis. A full summary of all pre-processing steps is shown in the table on this slide. Finally, we took several steps to ensure data reliability. First, we acknowledge that not all data points are equally reliable. For instance, meteorological readings and human factor attributions can be biased or missing. Following this, we standardize ambiguous fields like heat source and use quantile capping to fix extreme or invalid response times, like negative arrival times. Furthermore, we cross-checked critical numbers, like burned areas, against the California fire stats. We also ran a correlation test between the number of personnel deployed and how quickly a fire was controlled. The results showed a significant negative correlation, where our R-value was negative 0.32 and our p-value was less than 0.05. More people on the ground generally lead to quicker fire control, and the fact that this relationship was statistically significant helps confirm the internal consistency of our data.
Our project presents a predictive model for fire incident severity using machine learning. Specifically, we use an improved light GBM framework. Our dataset included over 87,000 fire incidents reported in the United States between 2019 and 2023. However, this posed several challenges. First, around 87% of records showed zero economic loss, which made traditional regression methods ineffective. Second, Critical variables like economic loss, casualties, and burn area were highly correlated, so we needed a much more sophisticated modeling approach. To address this, we first redefined the problem using a new target variable called severity, constructed as an ordinal classification using a combination of binning strategies and an analytic hierarchy process. We assigned higher weight to casualties, followed by economic loss and environmental damage, with a consistency check that confirmed the validity of this prioritization. In order to address class imbalance, we applied smote-atomic sampling, which boosted minority class representation from 3.7% to over 15%. In terms of feature engineering, we applied a wide range of pre-processing techniques, including one-hot encoding, target encoding, cyclic transformations, log and box-Cox transformations, clustering, and Gaussian-based spatial features. For example, arrival mins, which is the time it took for emergency personnel to arrive, was box-Cox transformed and adaptively binned to reflect its nonlinear impact on severity. Additionally, we enhanced the light GBM algorithm by introducing two key innovations. The first is dynamic histogram binning, which adjusts the number of bins based on the importance of each feature in real time. For example, if arrival mins becomes more important during the training, its bin count increases from 256 to 384 to better capture the nuanced effects. The second is asymmetric Gauss sampling, which gives more weight to high-severity events by adjusting the sample inclusion based on the gradient size. This strategy boosted the model's recall for serious incidents from 35% to 52%. Compared to standard models, our approach outperformed both logistic regression and random forest, achieving a 78% accuracy and a 0.77 F1 score, all while training in only 62 seconds. Feature importance analysis revealed that arrival mins, acres burn, and air temp as the top predictors, with arrival mins contributing the highest SHAP value. Finally, our partial dependence plots revealed a very important insight. When emergency response time exceeds 27 minutes, the probability of a high-severity event increases very sharply. Based on this, we recommend that fire departments aim to keep response time under 25 minutes, ideally leaving a 2-minute buffer time to avoid the danger zone. To support use in the real world, we also developed a real-time prediction system that can aid emergency responders in allocating resources much more effectively during critical situations.
To characterize wildfire risk, we looked at 4 main attributes: severity, likelihood, spatial distribution, and expected economic loss, while also quantifying model uncertainty. Starting with wildfire severity, we defined a number scale from 0 to 8 based on duration, size, suppression delay, and structural impact. Our classification model, trained on labeled data from CAL FIRE reports and relevant satellite inputs, shows a significant upward trend in incidence of high-severity events. The annual growth rate of fires rated severity 6 or above is approximately 12%, with a statistically significant p-value of 0.003. These high-severity events are increasingly concentrated in certain ignition types, particularly unattended debris burns and electrical malfunctions, with 70% of severity level 7+ fires linked to just 4 ignition causes. Using the SHAP mean, we calculated variable contributions to severity classification. The most influential predictors include wind speed, vapor pressure deficit, and suppression delay, followed by fuel moisture and housing density. Notably, the model identifies strong nonlinearities, especially for temperature and VPD, indicating threshold effects around critical dryness and heat levels. Turning to fire likelihood, we built a predictive model to estimate the probability of a fire reaching a severity level of 6 or higher. Predictor variables include vegetation index, temperature, precipitation anomaly, proximity to the urban interface, and day-of-week indicators to capture anthropogenic behavior. The probability distribution reveals heavy-tailed risk. Although only 14% of fires are expected to exceed severity 5, they account for nearly 80% of expected structural damage. We validated this model using a 70-30 training test split, achieving an AUC of 0.86 and a Breyer score below 0.12. Partial dependence plots highlight a sharp rise in risk above 35 degrees Celsius mean daily temperature, and when humidity drops below 10%. Our stratified likelihood table confirms this. For fires with above threshold temperature and sub-threshold humidity, the chance of reaching severity 6+ rises from a baseline of 14% to 41%. On spatial distribution, we applied a geographically weighted regression to map local heterogeneity in predictor-response relationships. The GWR results show spatial clustering in residuals, indicating regional bias in traditional models. For instance, fire-prone zones in Butte, Lake, and San Diego counties exhibit coefficient magnitudes 1.3 to 1.7 times higher than the statewide average, particularly for topography and fuel moisture indices. Regarding expected economic loss, we developed a weighted formulation using severity probability distributions. Specifically, we used the equation shown on the slide. Severity level 8, though rare, carries an expected loss of over $18 million per event, due to exponential increases in suppression and reconstruction costs. When spatially aggregated, 22% of census tracts account for over 65% of expected loss, suggesting highly skewed exposure. Finally, we quantified uncertainty in both predictive and structural terms. Epistemic uncertainty, derived via ensemble variance, is highest in fire-prone but underrepresented regions like Siskiyou and Modoc. Aleatoric uncertainty, modeled via residual entropy, is elevated during extreme weather anomalies.
Our risk assessment leads to a clear set of data-driven recommendations across 4 key domains. First, in fuel management and land use, reducing vegetation through prescribed burns and thinning is essential to lowering fire severity. Actively managing fuel loads leads to smaller, more controllable fires. We also recommend stronger land use policies in the wildland-urban interface, like enforcing fire-safe building codes, maintaining defensible space, and limiting development in high-risk areas. Our models show that reducing exposure and ignition sources directly lowers expected damage. Forest restoration and power grid hardening are also high-impact strategies, and our IOP analysis confirms that upfront mitigation reduces future suppression costs. Second, wildfire response must be risk-aligned. Allocating more crews and air assets to high-risk areas, especially on red flag days, can significantly reduce response times and damages. Enhanced early detection via satellites, lookout cameras, and real-time coordination can further improve outcomes. Our regression analysis shows that even small gains in response time can have large effects on fire size and impact. Third, integrated technology is critical. AI can now detect ignitions from satellite and camera feeds in real time. Drones with thermal imaging also provide live intelligence and can support suppression efforts. Predictive modeling based on weather and fuel data enables proactive staging of resources. GIS and communications tech improve coordination and safety. Tech-enabled firefighting is faster, smarter, and more effective. Finally, policy and funding are key. A national wildfire mitigation fund could support fuel treatments, home retrofits, and evacuation infrastructure. Insurance and public education could incentivize risk reduction. Because fires cross borders, coordinated interagency strategies are essential. Our models show that these combined efforts, including prevention, fast response, tech integration, and strong policies, can significantly reduce wildfire risk and future losses.
In conclusion, by integrating machine learning and risk analysis into a mathematical model, we have developed a data-driven approach to wildfire mitigation.
Our recommendations lead to faster response times, better resource allocation, and smarter policies. This will ultimately save lives and reduce costs.
This is how AI and actuarial science can work together to create a safer and more resilient future against wildfires.
Thank you for watching!